Again, thank you for the kind invitation, and somehow send a sign if you don't hear me or if there's a technical problem. So what I'm going to do in the next 20 minutes, I'm going to try to share with you our vision of modern transplant in the regenerative medicine era in the first half of this presentation. In the second half, I will briefly illustrate which are the research tracks we are working on here at Wake Forest. With regards to the vision, this is how we see the history of transplant. We think that we can identify three phases. The very first was all about surgery. Somebody had the intuition that a terminally diseased organ may be replaced using a viable functioning organ coming from either another individual or another species. So in those days, the most important thing to prove was technical feasibility, and that was accomplished. However, the problem in those days was that success was not the usual outcome, and this due to the lack of an adequate anti-rejection regimen. What changed the face of transplant was the introduction of cyclosporine, and this event allowed transplantation to transition from the experimental to the clinical era and basically made transplantation one of the greatest achievements in the history of medicine in the past century. In those days, we learned how to do transplant, we learned how to manage the medications to prevent the rejection, but we also figured out that the magic stick, so the instrument that has allowed transplantation to become a formidable clinical reality, and that initially is our friend, as years go by after transplant, actually turns out in becoming our main enemy. Why? Because yes, we can do transplants successfully thanks to immunosuppression, but we have to pay a toll. And one of these is the fact that we have to induce in the patient a new clinical syndrome that basically consists in the myriad of side effects that come with lifelong anti-rejection medications. So somebody had the intuition that probably the way to go in transplants should be to do transplant without immunosuppression. And so tolerance became the holy grail in transplantation. However, given the outstanding results and the excellent outcomes of transplantation, we expanded the indications to transplant. We expanded the donor pool. We also invented new types of transplants. Just think about face transplantation. However, to those who are familiar with what's going on in the field of regenerative medicine, it's quite obvious, it's crystal clear that we're now transitioning towards the third phase of transplantation, which is the regenerative medicine phase. And why is this? Because no other field out there in health sciences more than regenerative medicine has shown immense potential to meet the three most urgent needs of modern transplantation, which are one, the identification of a potentially inexhaustible source of organs, two, immunosuppression-free transplantation, so tolerance, and three, organ on demand, which is a concept that we recently introduced and basically consists in allowing the patient to receive a transplant when the diagnosis of end-stage terminal disease is made without any need for the patients to be registered in the waiting list where it could stagnate and face a clinical a risk, a mortality risk. So we are really in this gray zone during which we are slowly but surely transitioning towards the regenerative medicine phase or era of the transplant history. So if we agree with this vision, and if we imagine the transplant field, transplant medicine as a company, we know well that the most important department for a company is the research and development departments, so the R&D. So for us, there is no doubt that our R&D should be regenerative medicine, because no field in health sciences has more interest than our field in fostering progress in regenerative medicine, simply because the future of no other fields more than our future will be determined and forged by by the progress that will occur in regenerative medicine. Just like we shared with the audience in a state-of-the-art paper that we published a couple of years ago in regenerative medicine. So we firmly believe in this at Wake Forest, but at the same time, we have observed that even the transplant world is addressing interest towards regenerative medicine and things that are changing. The last 15 years, we have noticed that transplant journal, but also the general literature is addressing very much interest towards one, the regenerative medicine papers, but also to this idea of marrying the two fields. Now, 10 years ago, in surgery, we came out with a manifesto paper in which we were proposing organ bioengineering and regeneration as the new holy grail for organ transplantation, and in which we imagined the two fields as two beautiful trees generated from the same seed and whose branches are finally now intermingling, simply because these two fields, they share the same parenthood, they speak more or less the same language, and we pursue the same objective. Also, in a more recent paper, while reasoning on the state of the art of kidney transplantation, we observed that yes, kidney transplantation has been traditionally immunosuppressive based, but it's becoming more and more discipline based on regenerative medicine concepts. Also, the big publishers are very much interested in publishing and releasing journals on this idea of marrying the two fields, and we've been probably the most prolific center on that front. These are some of the books that we've been publishing in the last decade. The two last of which are these, organ repair and regeneration, in which basically we are proposing organ preservation as one of the most important platforms where the two fields merge. And so for the application of regenerative medicine technologies into transplant medicine. And more recently, in April 2022, the first volume of a new series, the Transplant and Regenerative Medicine series, has been released. This is a series that Elsevier, an academic press, invited me to lead. And the first volume has been edited by Wayne Author. The next, On the Liver, is about to be released next year. Also, transplant conferences are granting more and more visibility and space to regenerative medicine. These slides, for example, summarizes the most relevant lectures that I was invited to give in the past few years at the most important international transplant conferences. Also, the most important transplant conference, all of them, they have now an established tissue engineering or regenerative medicine community of practice or committee. Also, a few years ago, AST, for the first time as a transplant society, allocated funds to research that was based on 3D printing, so very much regenerative medicine oriented. And finally, the last piece of the puzzle is finally being inserted in these days as we speak. What does this mean? It means that the AST, the American Society of Transplant and Tissue Engineering, and term is the Tissue Engineering and Regenerative Medicine International Society, 2 years ago, in January 2021, they signed a letter of collaboration that launched for the first time a co-sponsored webinar series whose ultimate goal is basically to bring the two goals to the two fields together, but also paving the ground for what's going to be the next major step in this direction, which is in collaboration also with a third player, the other big regenerative medicine society, ISCT, the launch of a new conference series, the World Conference of Transplant and Regenerative Medicine, whose first edition very likely will take place in 2024. We are working on it under the form of a summit that will bring together the 50 most influential authors from both fields. And the overarching goal will be to brainstorm the status quo of the two fields and come out with a roadmap that should lead as soon as possible the delivery to the patient bedside of finally organs biomanufactured from patients' own cells. Now let's speak about the research that we do at Wake Forest. We are lucky enough to conduct our research at a world-class facility, the Wake Forest Institute for Regenerative Medicine, WFIRM, which is an innovation and translational hub. So our team works mainly on three different tracks: AKI, organ preservation, kidney preservation, and biofabrication in the form of decellularization technology, 3D printing, and physiomimetic systems. With regards to AKI, AKI is clearly the holy grail in nephrology medicine, but also one of the holy grails, if you want, in renal transplant medicine. In 2014, we started a pilot trial that we label as the double R study, where the two R's stands for regeneration and repair, in which we were using what we think is the best possible platform where to study how the kidney works and function once it's exposed to damage, which are the AKI and DCD renal allograft receivers. And we were doing this using RNA-seq technology conducted on the peripheral blood of the patient. We came out with our preliminary data on a nice paper in Annals of Surgery, in which we reported about the identification of potential genes responsible for regeneration and repair after damage. And that paper and those efforts and those data paved the ground for the next step that we are conducting now, in which we focus actually on DCD allografts, simply because now the DCD population accounts for 40% of our kidney transplant recipients. And we do believe that it's really probably the best platform, clinical platform, where we could study maladaptive and adaptive repair in the kidney after damage. What we're doing now, we're not limiting ourselves to RNA-seq conducted on the peripheral blood, but we're also conducting single-cell analysis on patient sample from biopsy of the patients, taking a baseline 1 month and 1 year. We are also conducting Raman spectroscopy analysis in the urine samples, and clearly we are combining this with the clinical outcome data, including cell-free DNA. And which are the ultimate goals of this effort? Is first of all, understanding which are the molecular pathways that needs to be activated after damage in the kidney. And the goal would be to identify a sort of magic stick that we can turn into a pill in a medication that we could administer to either our patient or to our graft, our marginal graft, in order to make them transplantable. And the second major goal is to develop an algorithm to be incorporated in a point-of-care device that should allow us, once we get a marginal kidney, to scan that kidney, and in order to understand whether that kidney should be transplanted or should be discarded. With regards to organ preservation, to my surprise, organ preservation still remains in transplantation one of the most important fields of investigations. And we've been investing and working in this field for now more than a decade through a collaboration with a company based in upstate New York called Bryonics. We've been using mesenchymal stem cells in order to mitigate ischemia reperfusion injury with very good data, both morphologically here as well as physiological. In the last few years, the last 3 years, we've also been assessing whether artificial mitochondrial transfer may be proposed as a regenerative and reparative tool in the setting of kidney transplantation. Keep in mind that this is a phenomenon that occurs naturally in vivo, and that's one of the tools through which stress cells can resolve their own stress. So we've been conducting a pilot trial in tandem with partners at the University of Turin. They took care of the in vitro parts of the study, and we took care of the ex vivo part of the study, consisting in the development of a porcine model mimicking the DCD renal allograft scenario. And we are in the process of wrapping up the data, and we hope that the manuscript will be ready for submission in January, and the first target will be biomaterials. And the results are very promising, both in vitro as well as ex vivo. Also, what we are very likely about to witness in the United States, one of the major revolutions occurring in kidney transplantation in this new millennium, consistent in the advent and the popularization of the uncontrolled DCD donation. It has been estimated that in the United States, we could produce up to 10,000 donors that are uncontrolled DCD. And if you do the math and you match with this data with the status quo, with what's currently going on in the United States, there is potential to almost double the number of kidney that we could transplant. So in January 2023, in collaboration with our local OPO or Honor Bridge, we will start the first trial in which uncontrolled DCD will be used in the United States. The idea is to enroll at least 10 donors for the next 2 years through the end of 2024. And the overarching goal is basically to prove that these initially untransplantable organs actually can be rendered transplantable. In other words, the UDCD platform is offering to regenerative medicine and transplantation a formidable platform where to prove that regenerative medicine technologies could be applied and could become very useful to transplant medicine. I received a message. I don't know if it's okay. And last, I'm almost done actually, is biofabrication. So let's start with decellularization. Decellularization is a technology that has become of age in 2008 as a technology, as a methodology to manufacture organs. And here at Wake Forest, we've been at the forefront of this technology. We've been the first in proposing porcine kidneys as a platform for kidney engineering, also discarded organs as a platform for kidney engineering. But actually, as years went by, we realized that probably the paradigm that justify this approach may not be correct. In fact, this is the paradigm. In theory, we have a patient, we get cells out of the patients. At the same time, we have an organ already existing, coming either from humans or mammals. So you decellularize those organs, so you get a scaffold. You see the cells on the scaffolds, and eventually you will transplant an organ manufactured from patient's own cells. I don't think that this is going to happen anytime soon, because this phase, this step, that is not really working the way we want for reasons that we do not have time to discuss. So probably the way to go is to change approach and propose 3D printing, because we need to start from the patient's anatomy. We need to understand the patient's anatomy, and based on that, build the organ. And so for us, probably the way to go is harnessing 3D modelization, artificial intelligence, and mathematical biology rather than relying on decellularization. Decellularization can still work to produce biomaterials, but we do not believe it's going to pay off at the end if we think about manufacturing organs. Clearly, 3D printing is a very nice story to tell, but it will require decades before we will reach the ultimate goal. What we are doing now, we are doing our first initial steps, and that consist in the printing of parts of structure of bioconstructs obtained from the ECM from renal ECM that can be printed and incorporated in the defect of the kidney. And what I can tell you, that's all I can disclose, the results are very good. We can observe renal regeneration, the regeneration of all the structures that exist in the kidney. And this paper is about to be submitted. Last, also, we are also working on the kidney on a chip for personalized medicine. This is an example of how it may look like. As you can see, all the parts of the kidney are recapitulated within. And I will conclude with this last slide that basically explains the title. The title has been inspired by a brilliant editorial that Dr. Atala was invited to write a few years ago in Tissue Engineering, which is a journal of PERMIS, the Tissue Engineering and Regenerative Medicine International Society, to celebrate the 25 years from the foundation of the society. The title basically explains probably what we are doing and why we are here today, and also what we've been discussing in this lecture. And the title is Organ Preservation, Organ and Cell Transplantation, Tissue Engineering, and Regenerative Medicine. The terms may change, but the goals remain the same. Thank you very much for your attention. And I'd be delighted and glad to answer your question if you have any. It looks like you don't. I do not hear you. If anybody's speaking, I do not hear.
Can you hear us now?
Yes, now I can.
I think there might be some feedback.
There's a big echo, yeah, in the background.
You can hear us here, right?
Yeah.
Yeah. So Tom, why don't you ask your question just here? It's easier.
Sorry about that. We were trying to ask you questions, but there's something with the Zoom link here. It's really just a high-level question about. I mean, there's a lot of technologies that you introduced in this sort of high-level introduction, which is great. What do you see as being potentially the immediate preclinical barriers to implementing some of these technologies in the clinic and convincing, for example, the payers who are going to need to fund this type of work, which is probably going to be more expensive than what we're doing?
Yeah, that's a good question. And actually, the first webinar that took place a year and a half ago of the webinar series that I mentioned before featured me and as a speaker sponsored by AST and Steve Badilak as speaker sponsored by Termis. And actually, he answered the same question, saying that's not going to be a problem. Cost is not an issue. Every technology at the very beginning is extremely expensive. Then things will settle down. But in terms of I'll answer also in a different way. Like I mentioned before, the decellularization technology is not paying off now. Actually, the pioneer in the field, Doris Taylor, the first of the main author, the PI of the paper that came out in 2008. Speaking about showing that you can produce organoids, cardiac organoids with this technology. Actually, she recently announced that she will be able, very likely, to deliver a cardiac organ, not organoid, a cardiac organ for transplant purposes in 4 years. So I think to go back to Dr. Badilak answer to the same question that you just asked, I don't think that funding and the cost will be an issue long term. Regulation is different. Going back to the example of the heart, the source for hearts that Doris is leveraging on is genetically modified pigs that are already FDA approved. So I think there are many hurdles if you want. I didn't show that slide. I have a slide on that basically contemplates 50 different hurdles, including regulation, including cost, et cetera, but all can be overcome.
Okay.
And thank you, Dr. Orlando. One question from the audience on Zoom. Erica Siren would like to know, what are the key clinical endpoints you'd like to see to make an untransplantable organ transplantable?
Well, first of all, it's renal function. It's not the rejection. It's mainly renal function. So basically, we want to see a kidney that at 1 year grants a similar outcome when compared to the standard with an SCD transplant. DGF is not really a major problem for us, also because these days we see a lot of DGF simply because we use a lot of DCDs, we use a lot of AKI. But to go back to the question, we should apply the same endpoints, the same criteria that we apply on a daily basis with the kidney we currently already do.
Great, thank you so much.